Hello, good morning, good afternoon, and good evening. Once again, this is Manolo S. Lover Jr., currently studying BS Electronics, and I'm currently fourth year college right now. So, this moment we will discuss about the project design or satellite or tower design about microwave communication systems analysis and design with satellite link. Okay, but first, we will discuss general objectives. So, our specific objectives right here, we will have the point or site A, which is Barangay Anahaw, Hinigaran Site A, and site B would be Talisay City, and it is located at Barangay Concepcion. So we will link applied to cable television system primarily, and we will aim to have also a we will provide a chosen areas with a high quality service through utilization of appropriate equipment, and we should attain the reliability of 99.9999%. And we have here our specific objectives. Those are the two sides at our line of sight where radio equipment tower would be located, to determine the operating frequency band necessary for chosen application, to determine antenna heights through the preparation of path profiles including the path analysis and calculations, to obtain optimum performance from a line of sight microwave system through frequency planning and establishment of necessary operational parameters, to attain a fade margin set in path calculations, which will be most economical through equipment configuration, to utilize a satellite link for the overall operation of the application, and to calculate the satellite's link budget. So those were our specific objectives at this design. So this time we will have our scope and limitations. So based on this graph, we will have the 29.2 miles of two sides separated. They are separated in 29.2 miles, and just like what I've said, from site A to site B, which is Barangay Concepcion and Barangay Anahaw. The microwave and satellite communication system link will utilize a single channel prior to the point-to-point transmissions of signals, and the operating frequency band will be based on the ITUR recommendation of F386-9 as provided in the specification sheet of equipment in order to achieve optimum performance of the system. So we will use the ITUR recommendation. Okay, so we have here our data of our site B, which is Barangay Anahaw in Nigaran. The topography and geography is 48 kilometers from Bacolod, and the land area is 15,492 hectares. And the number of barangays were 24, and there are 88,909 as of 2020 census. So the accessibility and transportation, we could use private vehicles or public transportation. So we use the main highway travels south from Bacolod City to Barangay Anahaw. Okay, so the climate in here is average temperature is 27 degrees Celsius. The maximum is 33 degrees Celsius for the month of April, and it reaches for 22 degrees Celsius from the month of February. And the wettest month is June, and the driest is February. So here, Hinigran Municipal Water provides the water in here, and the communications were Dito, Globe, Smart, and PLDT if it's in internet. Okay, so don't dig deeper at that there. So okay, here we go. We have here our site B. So here our site B is Barangay Concepcion, Talisay City, and our topography is 15.5 kilometers from Bacolod City, and the land area is 20,118 hectares. And the number of barangays were 27, and the population is 108,909 from 2020 census. So the accessibility of transportation, it is 31-minute drive from Bacolod. You either use private vehicle or public vehicle. You could pass through Burgos or Bacolod Airport Access Road. So the climate in here, the average temperature is 29 degrees Celsius. The reaching temperature of the hottest is month, which is 33 degrees Celsius, and the coolest month is on February, which is 24 degrees Celsius. The wettest month is June, and the driest is February. Okay, so the electricity is Seneco, same as here as Bacolod City, and the water district is Talisay Water District. Okay, and our communications right there is Talisay City. It includes telephone, PLDT, or globe line. So take this note. Okay, so PLDT and globe lines, and our mobile will use Ditto, Globe, or Smart. And yes, so that's it. The internet is Globe and Smart. So here is our path profile, and right here, I hope you could see my pointer, and it's very visible enough. So we have here our 490 feet. This is the obstruction in Barangay Granada at Alangilan Road. It is where located at the least part. So here's the part of Concepcion which is 482, just like what is having here in summary table. And right there is our, what do you call this one, is the Barangay Anahaw, Hinigaran, which is having 83 feet elevation. So this is our summary table. So Site A, Barangay Anahaw, it is 27.6 miles away from obstruction, and the elevation is 83 feet. Site B is 1.6 miles from obstruction, which is from Barangay Concepcion, just like what I've said. It is 482 feet elevation, and our obstruction is from Granada, Bacolod City, 490 feet elevation. So this is their coordinates, and yes, that's it. And this time, this is the satellite system block diagram. So this is from satellite. The tower will receive the signal or the data, and the tower is our receiver. And once the receiver, the data receives, and here we goes to the switcher, and the switcher can be transmitted through digital or analog. So when we use analog, we just simply relay those signal into our combiner, but if we use digital, we simply use encoder before transmitting it by our modulator to combiner. Okay, so this is our set-top box block converter diagram. Okay, so we'll not just explain this further because this is just a simple one. So just to make this thing short, here we have our storage, and we can use USB, SD, and our tuners eliminate loopholes from cable and satellite and something like that, more on signal. But we have here HDMI and input and output, and the power mains from AC DC controllers or power discretes. But the important thing in here is the human interface and signaling, so that we could monitor this one. So we have here keypads, buttons, and LEDs for monitoring, and also here for sensor and actuator. This is more on safety and monitoring. And I guess this is just a simple one for setting up a block converter diagram. Okay, so this is our overall block diagram. Just like what I've told before, from modulator we use just simply analog, and here digital. I'm sorry I forgot to tell you that this digital is having color blue, and analog is having modulator, which is color green. And here we will gonna see that This amplifier from combiner will go to trunk line cascading amplifiers, which they have their splitters and directional couplers, so that we could split them. And the transmitter right here is will be put in a tower by having those antennas, and will transmit it to our receiver, and our receiver will also have a top of to set top box. Okay, so here is our UDA15W71AB trunk line antenna. So ultra high performance, dual polarized, it's 15 feet diameter. And this is our SATCOM low noise. So this SATCOM low noise is the LC4000 series C-band low noise amplifiers are especially designed for satellite earth station receiver front ends and other telecommunications applications. So high performance models are available in severe standard frequency ranges with noise temperatures from 30, 35, 40, and 45 Kelvin. All noise temperature specifications are guaranteed over the full bandwidth of LNA and are verified cold load testing. Okay, so this is our SATCOM, and we have our table for their noise temperature and its operating frequency. Okay, so here are our 4.5 meter prime focus receive only antenna. I'm so sorry. So maybe I can't see it well, so we'll move me first. So I hope you can see it better now. So right now we have here our operating frequency for C-band is 3.7 up to 4.2. Okay, so that's it. We'll now go to Cadmium Networks PTP820C microwave radio. So this time, wait a minute. Okay. Wait, let me grab some materials right here. So here is our Cadmium Networks PTP820C radio. This PTP820C is an all-outdoor multi-core unit. The PTP820C has dual-core functionality, enabling the system to operate up to 2 gigabits per second via software upgrades, eliminating the need for future forklift upgrades or major system overhaul by the network operator to deliver gigabit plus capacity. So would be our basis for what we're gonna use about. So yes, this is the table that we're gonna use in problems or solutions. Okay, so let's move on with this one. So here's our power system block diagram. Our primary source is AC, and we have here generator. So those power supplies, we have circuit breaker with it, and those circuit breaker will give us an assurance and safety for our devices. Okay, so we have here automatic transfer switch. If the primary source is not operating or just having a brownout, the generator will supply the power, and the automatic transfer switch will be the one who will switch it. Okay, so we have here automatic voltage regulator right here to maintain the power, and we will not having exceed voltage that will, what do you call this one, we will destroy our equipment. So here we have here our battery to sustain extra power, and in case of generator won't work anymore. So that's it, that's why there's battery. So automatic transfer switch, just like in here, this is the one that we will use with something that would still sustain the power if there is an interruption of power. So we have still, there's still another UPS right here, and this UPS is uninterruptible power supply. So as you can see, we have here a lot of sustainable power, so that we could really have a great service, so we could satisfy our customers right there. Okay, so we have here our rectifier and inverter, so that if we use AC to DC, yeah, we could right away use it right away. And if you want to use DC to AC, we could simply use it. So we have here our main distribution panel. This main distribution panel is our like a mother electricity. Let's just call it like this. So this is the one that will manage the power, and when it distribute it, we have here our circuit breaker again to have a safety circuit breaker that will avoid the destroying of our devices in case of there's or power surges or backfiring of electricity or short circuit. So that's it. And we have here our equipment, aircon, lights, and outlets. We have here aircons because we need to maintain the temperature of our equipments, and also lights and for the people in there that needs the maintenance. Okay, so we have here our microwave calculations. So we've already discussed this one. Just like this one, the site elevation is from site A is 83, and elevation from site B is 482, and the obstruction of elevation is 490 feet. So this is our graph right here. So here is how to solve the Fresnel zone. So D1, D2, distance from obstruction 1, distance from obstruction site B, and we will have here the total distance and our operating frequency. So we have here the final result of 31.87 feet. So here how to find the total height of obstruction. So we will just simply add the Earth's curvature right there, and the total height of, what do you call this one, the height of obstruction, the F1 right here, the Fresnel zone, and we simply add 40 feet right there, and we have here the total height of obstruction, which is 583 and 0.95 feet. So this is more on calculations. Oh, wait a minute. Here. Okay. So the antenna height, we will just simply what do you call this one? Find the value of height, and we have here the final answer of 123.81 feet. Okay, and assuming B is equal to 15, we have here the antenna, the tower height, 131.31. Okay, so 131.31 feet. So the tower type is three-legged self-support tower. I'm sorry. Three-legged lattice self-support tower, and the free space loss is 143.68 decibels. And the tower type, just like it, and rigid waveguide length is 143.81 feet by adding the height and the 20 feet, and the flexible waveguide length in 5 feet per side. So waveguide loss, Flexwell elliptical waveguide, just like what we told before, we use the table. So we have here 1.78 decibels, and waveguide length is 3.81 decibels, and our connector loss is 0.5 decibels. Radome loss is 0.5 decibels. How to add the total fixed loss is simply adding the waveguide loss and connector loss, radome loss, and we have here the total of 4.81 decibels. Our total loss right here is the multiplying the total fixed loss into 2 and adding the free space loss, and we have here the total of 153.30 decibels. So here are the received signal level. This is situational by trying and trial and error, but here the actual gain is, we will just simply use 15 feet diameter, and We have here 20 log multiplied into our operating frequency multiplied with our diameter and just simply add 7.5. We have here the total of 48.8 decibels, and our actual gain right here, we will just simply multiply the total actual gain times 2 is equal to total gain of 97.59 decibels. Okay, so here is our net path loss. We will just simply subtract the total loss with the total actual gain. So we have here the 55.71 decibels, and our output power is 30. The medium receive power is simply subtracting the output power, and we have here subtracting the output power with the net path loss, and we have here the medium receive power of negative 25.71. So here our practical threshold, it's 85 negative 85 decibels. So the fade of margin, we will just simply subtract fade of margin minus with medium receive power, and we have the total of negative 59.29 decibels. And here is our reliability. So we sum it all. What do you call this one? It's 0.05 times multiplied by operating frequency. This is our operating frequency, and this is our distance, and we will just simply multiply it into 10 to the power of negative fade of margin over 10, and here we have here the result, which is 0.9996055 times 100, or we have here 99.9999%. Okay, so we have here, we're done now with our calculations. Let's see our datasheet summary. So here's our operating frequency, which is 7.74 gigahertz. The Earth's curvature is 22.08 feet. The Fresnel zone diameter is 31.87 feet. The total height of obstruction is 490 feet. The antenna height is equal to 123.81 feet. The tower height is equal to 100. Oh, I'm so sorry. So the antenna height is 123.81 feet. The tower height is equal to 131.331 feet. The tower type is three-legged self-support tower. The free space loss is equal to 143.68. The rigid waveguide length is 143.81 feet. The flexible waveguide length is equal to 5 feet. The waveguide loss is equal to 3.81 decibels. The connector loss is 0.5 decibels. The radome loss is 0.5 decibels. The total fixed loss is 4.81 decibels. The total loss is equal to 153.3 decibels. The receive signal level is equal to negative 30 decibels. The parabolic dish diameter is equal to 15 feet. The actual gain is 48.79 decibels. The total actual gain is 97.59 decibels. The net path loss is equal to 55.70 decibels. The output power is 30 decibels, and the medium receive power is equal to negative 25.71 decibels. The practical threshold is negative 85 decibels. The fade margin is negative 59.29 decibels, and we have the reliability of 99.9996055%, or 99.9999%, which is part of our objectives. Okay, so here's our satellite footprint performance parameters. So we have here our C-band. Oh, wait, maybe we aren't able to see it. So we have here our C-band, and we have here the 36 megahertz transponders, and we have here 28 number of transponders. So here's our global beam EIRP. So as you could see, we have here what do you call this one? We have here 40 decibels. So you can see in the number decibel watts. And here our satellite link budget calculation. So the downlink frequency is 3.95 gigahertz. Effective isotropic radiated power is equal to 40 decibels watts. And range of satellite from Earth station is 22,369.36 miles. The terminal gain to temperature ratio for Earth station is 2.6 decibels per kilo. Kelvin. So the free space loss, yeah, just like what we used to do before. So 96.6 plus 20 log multiplied into operating frequency plus 20 log multiplied into range of satellite from Earth station. So we have here the total free space loss of 195.52, and here our EIRP, or we have here 40 decibel watts, and our free space loss is just like what we told before. We'll just simply add all these losses, the other losses, satellite pointing loss, off contour loss, atmospheric absorption loss, rainfall loss, polarization loss, terminal pointing loss, and we have here the isotropic receive level. We total it. The terminal gain for station is 2.6, and the sum. So we have here negative 52.92 decibels watts, and we have here adding the 226.6 decibel watts by Boltzmann's constant, and the carrier to noise ratio is 73.67 decibels. So here is our downlink datasheet summary. So we have downlinks frequency is 3.95 gigahertz. The EIRP is equal to 40 decibel watts. Wait a minute. I'm so sorry. So the terminal to gain temperature is equal to 2 decibel per Kelvin, and free space loss is equal to 195.52 decibels. Satellite pointing loss, off contour loss, atmospheric absorption loss, rainfall loss, terminal pointing loss is equal to 0.5 decibels, and isotropic receive level is equal to 155.52 decibel watts, and and our carrier to noise ratio is equal to 73.67 decibels. So I guess you are learning how to, well, you have any ideas on what is our design right here, and you may comment down below to have any further questions, and I hope we could add some more videos after this presentation. So thank you and goodbye. Maybe we'll locate soon our land, or the side A, side B, and our obstruction. So thank you for listening and goodbye.